Here's the awkward part. Good morning, everybody. I'm going to give a few seconds for people to roll in. It's 10 o'clock on the dot, and I'm aware that some of you can't hear us talking for up to a minute. So I'm just going to fill some airtime right here. It is January 18th, and you have made your way to another Lighting Design Lab webinar. This time, for the first time, we've had several firsts for the past several webinars. We get to learn about how to use Manual J and Manual S for residential HVAC applications, which I'm very excited about learning. And Chris Morin, who is the founder of, now, Chris, do you say HVAC or do you say HVAC or do you say HVAC Pro Blog?
HVAC. Okay.
And an advisor to Conduit Tech and sales manager for Mitsubishi and a veteran of the U.S. Marines. So multi-hyphenate. Chris Morin is here to educate us, and Shelby Breger, who also co-founded Conduit Tech and is a Breakthrough Energy Innovator Fellow, which seems pretty prestigious to me. So happy to have them both here. And a little bit of housekeeping about our webinars and GoToWebinar in general. If you haven't been to one of our webinars yet, you guys are all on mute, the audience is on mute, but we do have the ability to ask questions. It might look like this questions box. It might just be that little question mark, that's what it's called, box, depending on what application type you're using. If you can't find either of these things, see if there's a flashing arrow on one of your screens and click that. It'll slide the toolbox out. We're recording this, and the recording will be available within about a week after this on our website. And there's a survey after class. Super quick, I think it's 10 questions, gives us your feedback, whether you want more of this, how much more of this you want, and we really appreciate when you take the time to do that. Upcoming several webinars that we've not offered before. So for Seattle area folks, there's a brand new emissions performance standard that's gone into effect, and there are about 200 people registered for this already. That it's going to be a very, I think, intense webinar. And then some fundamentals of strategic energy management, and then specifically 50,001 two programs that the DOE has. And then we don't have all the details yet, but on February 29th, PAE engineering firm here in Seattle is going to talk about a heat pump water heater retrofit they did down in Occidental Square. So that should be very interesting. You'll be able to click these links when you get these slides on our website later. And I'm not going to talk too much about these rebates. I want to get started to get Chris enough time, but these will be available for you to explore when you get the slides too, sort of related to what we're talking about now. And let's see. I'm going to hand it on over to Chris, and while he brings his presentation up, Shelby's going to do a little introduction. Maybe a big introduction, I don't know.
No, don't worry, I'll keep it quick. We're here to see Chris. Well, I'm here to see Chris at the very minimum. I think everyone else here is too. And what I gotta say is I cannot think of a better person to lead this session. First, I'll just start with the logistics really quickly. We will be taking questions in the chat. I will be accumulating those and moderating those for Chris. So please do ask anything that's top of mind. I know we have a mix in the audience today of HVAC, affiliated professionals, energy efficiency professionals, all range. And so there's no dumb question here. This is all about how can we really move the industry forward and support the incredible work that everyone in this community is doing. So with that, I'm excited to introduce Chris. Chris is an incredible Manual J, Manual S, Manual D, all the manuals expert, but he's more than that. He is a trainer and teaches so many pros throughout the country. He has been a contractor himself. He has been a trainer and still is. He's an area sales leader for Mitsubishi and is a veteran. And most importantly to me, obviously, he is an advisor to Conduit Tech, which is the company I work with, and where we're really committed to building the tools for the HVAC community. And everything that Chris does is around moving the industry forward. And so with that, I'm going to hand it over to him to sort of share with us how we think about system sizing, system design, and also as we think about this community, just how do we move energy efficiency and electrification forward well. So with that, over to you, Chris.
Oh man, Shelby, every time you do this, it's such a nice introduction. I really appreciate it. So yeah, like Shelby mentioned, I am a regional manager for Mitsubishi Electric full-time. So you might see a couple of references to that stuff today. Of course, for the last almost 15 years, I've been an ACA design instructor, which means I've been helping thousands of HVAC contractors across the country with manuals J, S, and D, which would be duct design. We're going to concentrate on the manual J and the manual S side today, right? And really what we want to do is give you a brief overview of load calculations and how it fits into building codes and what's required, right? Also, we want to spend some time on the things that impact the loads the most, like the two major things, temperature difference and infiltration for heat loss, and what you should be using in the load calculation software to get the most accurate calculation, right? Because it is a calculator. And then we'll talk about the cooling side, because there's two other things that impact the cooling gains the most, solar heat gain and internal gains. And then we'll talk a little bit about the technical side. We're going to talk about manual S and particularly selecting equipment using manual S for variable speed heat pumps and for air conditioners. Please, like Shelby mentioned, Q&A. If you have a question as we're going and it's really important, Shelby will stop me, which is good. I want that to happen. And there's some obvious spots, like when we finish up manual J, I'll see if there's anything going. And then of course we'll roll into S before I turn it over at the end to Shelby. So that way she can tell you about how all of the troubling things I'm talking about, Conduit Tech makes it so easy for everybody now. All right, so I am not a great storyteller, but I do like to talk about some of my past and how it relates. So if you didn't notice, you're in my home office today. I got a few memorabilia things behind me. Not the Captain America shield. I got that for Christmas one year from my wife. But in Parris Island, once we finish boot camp in the Marine Corps, we actually go to Camp Geiger on the East Coast, right, where we learn Marine combat training. Part of Marine combat training is learning how to use a compass. And an interesting thing, if any of you have been in the military and you've ever used a compass, there's usually a course that you use, right? And of course, I'll keep this PG because in the Marine Corps, they like to use that sailor terminology, but we learn how to use compasses at night. And the deal is you go in the woods with a buddy, right? They tell you the first azimuth, like you can see the guys telling the Marine in the picture here. And the two guys go into the woods with all their gear, and you walk, as long as you walk on that azimuth, you're going to reach basically a mailbox in the woods, open the mailbox, and you get the next azimuth. And the deal is when you finish the course, your team can now go to sleep. Unfortunately, what most people don't realize is you'll never finish the course, even if you did it perfect, right? But me, I wanted to hurry this along because it's been an exhausting day. We were at the ranges, we were cleaning weapons, it was all that stuff, right? So I talked my buddy into trying to head out in the same direction everybody else was heading out to before we talked to the sergeant in charge. And we'll just say he put his arm around me after I did a few push-ups and a few other things. And he told me the time to have the map was before you enter the woods. And this is some great advice that can be like life-changing if you take into account in every other aspect, right? But this, when I teach a full design course, is what I like to talk about when we refer to Manual J. ACA Manual J is the map you need in order to select the right equipment, to size your ductwork, to set the system up correctly for quality installation verification procedures. Like if you don't have the map before you enter the woods, there's no coming back from that, right? And it's amazing how many contractors, unfortunately, don't do this as the first step in some of their sales processes, right? And it's because it's time consuming and they may not be knowing what they're looking for. They take a lot of educated guesses or uneducated guesses, and they end up with the wrong map sometimes. So we want to correct that, and we're going to talk about the things that impact the map the most. All right, so moving right along. So really, this is building on, you know, getting your sales process correct, right? And we want to be able to have the right framework in order to evaluate the house. And when you're doing this and you're using software like Conduit, you're actually going to build value on site with the homeowner. And you're going to actually sell the right system, right? So it's really hard to sell the right system if you don't know how big it needs to be or how small it needs to be. But people do it every day, right? And it doesn't matter where you are in the United States. It's unfortunately a very low percentage, and we're working on that, all right? So we want them to sell the right solution, and not just because it's the right thing to do or it helps the contractor to sleep at night, but because it's a code requirement, right? It's part of the International Residential Code and the International Energy Conservation Code, and it's been in place as far as my library goes back. I mean, obviously mine's only about 15 years or so because that's how long I've been teaching this. But you can see, and I'm not a big slide reader, but I'll read this one because it's code, that all heating and cooling equipment shall be sized in accordance with ACA Manual S, remember that's equipment selection, or other approved methodologies based on building loads calculated in accordance with ACA Manual J or other approved heating and cooling methodologies. Now, what a lot of people don't realize is residentially, there's not very many other approved methodologies, and it's really up to the building inspector to approve some other methodology. And most of them don't want to take a stab at something that they don't know. So therefore, ACA Manual J version 8 is what you should be using. And remember, this is the residential design process. I'm going to assume, and I heard some great titles at the beginning, even though some people are outside of the industry, they have some awesome building knowledge. So I would assume you guys know system concept. We're going to skip over ACA Manual RS today. This is like, am I using a boiler or a furnace or a heat pump, right? Very basic. We're going to go right to load calculations. So that's Manual J. If you were going to work on the commercial portion or the opposite of it, there's a completely separate manual and process and calculation. It's Manual N, right? And this is just one piece of the design process. Remember, it's the first piece. So if we don't get the first piece right, it messes up the rest. We have to get this right. We have to know if we're going to zone the system out, whether it's zoned with equipment or ductwork. We have to know how we're going to get the ductwork where it needs to go. That's Manual T, right? Then we select the right piece of equipment. Then we size the ductwork if it pertains. And then, of course, we adjust, test, and balance the system. We make sure all the air goes back to the unit to remove moisture and cool the air, and then goes to the space that it needs to go to, not just heat and cool your attic, right? So really important. That's the direction we're moving. We're focusing on J and S today. So what do we need to understand in order to do this calculation? The four major things that impact the heat loss and the heat gain the most, the ones I already mentioned: temperature difference and infiltration or air exchanges per hour, right? That's on the heating side. And then on the cooling side, the solar heat gain, which is really important on fenestration or windows and glass doors. And then, of course, internal gains. And this is where I see a lot of people, how to say this politely, mess up, we'll say. They either forget a lot or they try to add a bunch. It's really crazy. I've been looking at load calculations and providing advice for well over a decade. And this is where I see the most mistakes. And it's funny because they know what size the system should be, but they don't get the math right. And when they do that, they tend to oversize it sometimes. All right. So really, if you pull a building permit, you have to make sure you do a Manual J load calculation. And it should be done in the whole structure, right? And you can do a block load if you're doing a system replacement. So that way you can verify the physical size that's needed for the system, right? But if you're going to do a new distribution system, whether it's ductless and it's laid out with a new distribution system that way, or it's ducted with a new duct system, you have to do a room by room load calculation. If you don't do a room by room, then you won't be able to assign the correct portion of volume of air to that room in order to heat and cool it, all right? And in order to do this math correctly, you got to use software. You might be able to do heat loss like with an Excel document and end up with the same number because it really is that simple. Temperature difference, surface area, U value of the wall or the door. That's easy. The problems really come into the heat gain side, and that's the cooling side, and that's how we actually select heat pumps. So with a focus on that, with carbon reduction across the country and rebates going up and all of these opportunities, we have to make sure we get this right in order for it to work for the homeowner. And that's really about providing comfort, right? All right. So let's talk about conducting a site survey. Remember, I was telling you how easy it is to do load calcs with a heat loss? That's because you just have to define the thermal boundary of the house and calculate the heat loss across those walls and doors and ceilings and floors. It's pretty, and windows, obviously. It's pretty simple, okay? When you start throwing things like the direction of the glass, heat that's generated in the building, skylights, or location of ductwork and how much heat is in that attic, all of these additional gains, you can't calculate simply. You have to use software, all right? And this is where load calculation software tends to get very complex, okay? If you don't do load calculations now, or you rely on somebody else to do it for you, you have to make sure that they have all of the information that's needed to do the load calculation correctly. Otherwise, they tend to just use the generic values that are set in Manual J or the software. Usually they don't set them to 0, it's set to some basic standard, and it's usually, unfortunately, too conservative. So over the last 10 to 15 years, I've developed a site survey form. I'm sure Shelby can make this available to anybody that wants it. It's 2 pages. It's a PDF. You can print them off. It's really to make sure you gather all the right information at the home if you're not going to do the load calculation there, so that way you don't forget to get any of the particulars, right? And you can see when I teach a full design class, we talk about all the construction details, the design temperatures, why, right? Ceiling characteristics and floor condition and the identifying the insulation based on what it looks like and the depth, all these different pieces, right? We'll talk about internal gains today, obviously. But on the back side is more information that you need to gather, right? Like the location of the ductwork. And this was a big change from version 7 in the 1980s to when we went to version 8 with ACA. When it comes to Manual J, version 7 in short forms just apply a generic percentage value of the load for ductwork. It's very loose and it's not accurate. Manual J version 8 actually includes the location, the configuration for surface area, the supply air temperature and the loss or the gains on that, how well it's sealed, right? How well it's insulated. All of these things impact the heat loss and heat gain. And if you don't do this right, you could be gaining a half a ton to a ton of cooling sometimes in an unconditioned attic, and you didn't account for it, all right? So that's why you have to make sure it's Manual J version 8, all right? And then of course, windows and doors. So what I like to do is actually print off a floor plan from my local town assessor, so it saves me a lot of time, and I can just draw the windows and doors right on that floor plan. I assume it's the same in Seattle, but almost every town across the country, if you just search the town and town assessor, it'll pull up a site that you can actually just download the property card from. It's all public information, which can be a little creepy sometimes. Just got to be careful what you actually are looking for there. If you've actually had a house that's been sold in the last, let's say 5, 6, 7 years, I'm willing to bet if you search that address on realtor.com, you can actually pull in a floor plan. And that's what I did for my house. Pictures of the floor plan. And like I said, creepy. Now people know which one's my daughter's bedroom, right? So it can really mess you up. All right, so let's talk about how to evaluate factors that drive the heat loss, all right? So about 75% of your heat loss is just purely temperature difference across devices. Unfortunately, if you use any sort of rule of thumb like square feet per ton, or we used to joke that there was manual E, you would hold up a sheet and there was a little cutout of a house. The bigger the house, the bigger the tonnage, right? It's not real, but it's just as laughable as square feet per ton. And if you use that, it doesn't take into account the infiltration of the house. And that could be as easily 25% of your total heat loss of the house. And then of course, on the cooling side, solar heat gain and internal gains, we'll talk about after we get through the heat loss side. So a couple things on temperature differences, right? We don't design for record-breaking weather conditions. In fact, Conduit uses ASHRAE Weather City data. It's the most accurate data we can gather, and we use the 1% design temperatures, which line up to table 1A in Manual J, right? That's where Washington's listed. 1B would be like microclimates like Arizona or Miami or Hawaii, right? Where we don't design the same because of really high or really low humidity. But it's really important that we don't just look at the outdoor design conditions, but we also design to the correct indoor design conditions as well. And that's set in the International Energy Conservation Code. So on the outdoor design conditions, the 1% or 99% design temperature means at any time throughout the entire year, let's say your design temperature is like, I think it's like 27 in Seattle, in that range. That means when you add up all the hours of all the days, it adds up to 3.65 days. It was less than 27 degrees outside. All right. And don't get me wrong, the correct size heat pump or furnace or boiler, whatever you're installing, is going to run all the time to try to maintain temperature. This happens in the northern reaches of Maine and the highest points in Minnesota. And we have heat pumps, like I was telling you before, I work at Mitsubishi. We have heat pumps as the sole source of heat. They work great because they were sized correctly for that building at that really low extreme temperatures down to as low as -13 Fahrenheit. All right. So outside design temp, we have to stop somewhere. We can't design around an extreme event. We can't design around to 99.6 degrees, right? Because in order to get to that point, the system would be so drastically oversized that even if it's variable speed, it doesn't ramp down far enough in the rest of the year, the other 98% of the time, in order to provide comfort. It'll short cycle. It won't remove moisture. The heat exchanger will get really hot and it might crack, right? There's all these things that happen with oversized equipment. And on the heat loss or heating equipment side, it really comes down to, did you get the temperature difference right? All right. It's so simple. You got to use those right temps. And that is one thing that building inspectors do look for. Okay. On the indoor design temps, we actually design around 75 degrees and 50% relative humidity and cooling. That's a standard in the code in every rebate program across the country, right? Of course, we'd like temperatures to be warmer in order to conserve energy. It might be cooler for some of us bigger guys. We might like it feel more comfortable when it's a little cooler. But at that temperature and relative humidity, it actually provides room for drift, where if it's an extreme event, let's say it's 95 or almost 100 degrees out, it obviously can't cool to 75 degrees, but the system is running all the time and it's removing the moisture. It might reach 76, 77 degrees inside, and it might be 45% relative humidity, and we'll feel comfortable. So what that is it's in the middle of the psychrometric comfort zone. It allows room for drift, and we do the same thing on the heating side too, where we actually heat to 70 degrees plus or minus 2. That's what's in the code. It goes high as 72, as low as 68. And if it's really cold out, furnaces or the boiler or the heat pump's going to run all the time, and it's going to start to dry out the air. To feel more comfortable, we can add humidity, right? And most furnaces I know in the Northeast and the Northwest typically have whole home humidifiers on them because of this, in order to provide that comfort. All right, so we talked about temperature difference. Let's talk about the other 25% that most people don't get right. And that's because they don't have a blower door. I don't know how many HVAC contractors are on here that have a blower door. I would love to see if you posted in the questions that you do. I think it's pretty rare if you're evaluating homes because you're an analyst or you're a verifier. Obviously, you have a blower door and you can see how leaky some of these homes really are. What I would say is, if you don't know what the infiltration is, you have to make an educated guess. And I would hope you take account into some things that you're seeing, right? So some visual cues of some leaky houses would be if there's a lot of dust accumulating in the insulation of the attic, right? Because when air moves through insulation, the insulation will pick up that dust. And actually, if you do weatherization, you know what I'm talking about. That's how you can easily find all those holes in the ceiling in order to seal it up, right? Obviously, talking to the homeowner and understanding if any rooms you feel drafts in. My house, I live in an old Victorian, 1880. We have some open fireplaces. It can get pretty drafty when we don't close those things, right? And the heat bill goes through the roof at that point. Ideally, we'd like to seal those off sometime. And when the house was built, if there wasn't any major remodels or retrofits, it actually falls into some generic areas as far as leaky or tight. And I'll show you those in a second. But when you're selecting the tightness of the home in Manual J, it's actually referring to the air changes per hour based on the size of the house. There's actually 5 selections. It could be tight, semi-tight, average, semi-loose, or loose. So those are the 5 options, and the air changes per hour you can see line up under the floor area or the heated and cooled space, right? If you're measuring air changes per hour, obviously you're measuring leakage at 50 pascals, and you change it over to air changes per hour with the blower door. If you're measuring it, you can just enter that number in any of the software. If you don't, you're guessing on one of these 5 construction pieces. And if you didn't know, Lawrence Berkeley Labs actually did a study back in the 90s on air tightness of US dwellings, and they included tens of thousands of homes across the country. And I did a little analysis, and what we found is based on the age of the house, if it wasn't weatherized, based on the construction type at that time, it fell into these buckets, right? So if the house was built older than 1950 and it's never been touched, it hasn't been weatherized, it's a loose house. Like my house before we did weatherization, right? It's semi-loose if it was built between 1950 and 1994. I know that's a broad range there. There's some things that happened in the 70s and the 80s when it comes to energy conservation, all right? Average for a home that's built 95 or newer. Semi-tight for an Energy Star home, and then of course tight for a net zero passive house. If you hear keywords like spray foam or it's so tight, we need ventilation, things like that, it's probably a tight house, all right? Now, if the home was weatherized since then, I would say you want to select the next one up at the best, right? So my loose house from 1880, we did as much as we could. When I did the blower door test, it was still leaking quite a bit because we can't just seal off all those chimneys and stuff. So now it falls into the semi-loose category, okay? We have a lot of semi-loose stock in the Northeast that were built between 50 and 94 that have been weatherized to about average. Most of the local weatherization programs, they do a decent job, but they purposely stop so you don't have to add ventilation to the house, right? Because it's a huge additional cost to get that right. So they only air seal it to a certain point. And I'm willing to bet it's the same across the country. All right. Ceiling condition. So this is another spot because it's temperature difference and the ceiling is such a large surface area that it impacts the heat loss quite a bit. And really, you have to identify a few key aspects with ceilings. You need to know if the attic is vented, all right? And not just vented, that it meets the FHA standard when it comes to ventilation. So not just that there's a gable vent at the end. Actually, if you didn't know, this is a picture of my attic after weatherization and everything's been blown in. It's got an R38 up there now. But it's one of those things where if it's not professionally installed either, it can really impact the effective R value of the ceiling, all right? If this is a roof ceiling combination, right? So if you have like the second floor of a Cape style home or a colonial and there's a vaulted ceiling, if the ceiling roof ceiling combination, you can only fit so much insulation in that 2x or 2x6 or 2x8 or even 2x10, hopefully construction. And the ceiling heat loss actually gets greater compared to just blowing in a stack of cellulose there, right? So there's some options on those forms and there's some options in the software. Just make sure you're actually seeing what the insulation value is. And really where I see guys go wrong here is when they have multiple types of insulation. So a lot of times you'll find there's some fiberglass batt insulation in an attic, and then maybe it's air sealed and weatherized, and they blow another 5.5 inches of cellulose on top of the batt insulation. In order to get this number correct, you need the total effective R value of the ceiling. So you need to measure the fiberglass insulation, let's say 6 inches averages out to be like R19. And then 5.5 inches of cellulose will give you another effective R20. The added of the two would be R39 for that ceiling. That's what I have upstairs, all right? Now, if you don't know what you're looking at, this is a great chart to have out in the field. Based on the depth and what you see, you can get the effective R value, and you just multiply the inches by the R value per inch, right? So like I talked about before, you know, if we had blown in cellulose, you can see loose fibers, it's gray, might be from newsprint, right? It's pretty obvious, it's cellulose, it's 3.7 times the inches. If I had 5.5 inches, that'd be R20. That's pretty close. I think I rounded on that one. All right. You know, it's funny, if it's commission, I get it exact. Anything else, I have to use a calculator. Anyway, if you didn't know, closed cell spray foam, which is what we're seeing a lot in new construction these days, has an R value of 6.5 per inch. So this is why you can actually get the air, the tightness of the home so tight with really high R value that it's almost like a balloon for new construction today, where you heat the house and there's nowhere for the heat to go. And the heat loss of the home is so low, the only way you can really effectively heat it and be comfortable without short cycling and stuff is using a variable speed heat pump, right? And that's why you're seeing a lot of this across the country. Okay, let's talk a little bit about ductwork. It may or may not be sealed, right? Especially on the existing stuff. Anything new, you got to seal it to code, right? But you do have to evaluate the condition, the location, and the materials of the insulation because that impacts the load, right? A properly sealed boot and flex fitting you can see on the front side here versus something that could be easily disconnected, unsealed, not sealed to the ceiling. Where that boot hits the floor or the ceiling, those flanges, those should be sealed as well to slow down the infiltration through that ceiling and floor from unconditioned space, right? So that all impacts the duct losses and gains, which impact the load. And I've seen this up in an attic easily be a half a ton to a ton additional sometimes when it's outside the building envelope. And then of course, fresh air. So you need to evaluate not just what the software tells you, but what local code tells you as well. And I apologize, I don't know what the local code in Seattle happens to be. I live and work in Massachusetts, so it's actually 1:30 p.m. where I am today. But there's 5 different ways in Massachusetts to calculate the fresh air needs of a home. So it can be all over the place. Typically, and I don't like to use rules of thumb, but usually when we talk about this in training, it works out to be somewhere around 15 CFM a person. Please don't jump in and tell me how that's wrong. I know, I get it, ASHRAE 62.2 and all the different options. Depending on where you're working, it can be a lot different. But make sure you're accounting for this. And the tighter the home, the more this is important. And obviously, in our climates, we share similar climates. We want to make sure we condition that, right? So we either want to run that through an HRV or an ERV if we can have balanced ventilation. That's a good thing. We don't want to rely on just all the air coming through the unsealed penetrations of a house like where I live right now. It's not quite as comfortable. All right, let's talk about the key factors for cooling now. So you can see solar heat gain can easily be more than 50% of your heat gain. The more windows you have and the more windows that face south or southwest, the higher percentage of the load this is going to be. Of course, internal gains, air exchange, which is infiltration, and temperature difference makes up the majority of the rest of the heat gain calculation. And I talked about it already with infiltration and temperature difference. So I'm going to hit the other two now, solar heat gain and internal gains. This is actually a picture of my office before we moved in. The point of this is to talk about windows and what you see outside, right? So when you're identifying windows and fenestration, which makes up more than half of your heat gain, right? The solar heat gain of the house. You need to start with the frame. Pretty basic stuff. You need to know if it's wood, metal, vinyl, insulated fiberglass, right? Very basic frame material. And then take a look at glass type. And this is one that's much harder to verify in the field if you don't know what to look for. So most windows out there, particularly the ones that are not in new construction homes, are most likely clear. If you're going to enter something other than clear, you should know for sure what you're entering. If is it heat absorbing, is it low emittance, low E, right? And this is typically identified from the NFRC sticker. And that's usually located in the top or the bottom jamb of the window, right? Or if you're doing something new construction, the sticker is probably right on the window still. Or ask the homeowner, because like in my house, we have 57 windows in this old Victorian. And it costs a lot of money to replace them. And I know exactly what that U value is, all right? The higher the U value, or I'm sorry, the better the U value, the more you're gonna end up paying, right? So ideally, we're getting the exact number. If we can't, we're gonna start referencing the charts in Manual J. There's a great reference, I think I'll show you next on from BPI, right? So bpi.org has an awesome chart to show you what, as you build the assembly, what the U value and the solar heat gain coefficient is for those windows. And when you're doing this, it's actually deducting that area from the wall, because actually the weakest point when it comes to heat loss or gain is the window off of that wall, right? So it's actually going to calculate the wall first when you enter the full dimension, and then on that wall, what's the window, the door, everything else that's on there. It's going to deduct from that surface area. It starts to increase the heat loss and heat gain of that wall because of those inefficient features. But it's great for lighting, right? All right, let's talk about a couple other things that impact the gains, which would be, believe it or not, exterior bug screens. So exterior bug screens can impact the load a lot the more the windows you have. The number of windows, if you don't enter this, you could add sometimes a half a ton of gain to your load, because that exterior bug screen, whether it's half the window or the full window, will actually deflect some of the sun hitting that window, right? And then of course shading. So internal shading, always, if you're not sure, like in a new construction home, or in this case, somebody's not living there, you would assume medium type blinds, half drawn, 45 degrees. That's the standard in Manual J. But if you see drapes, then you enter drapes, because that's what we have here today, right? And believe it or not, there's a big difference in gains with dark out shades, right? The ones that are put in most bedrooms versus some of these that are more sheer, right? So get that right. So when you're identifying the number of panes, there's actually an easy trick. It's pretty simple. You look for the reflection. I like to use my iPhone. I set the flashlight to the highest setting, and I'll just hold it up to the corner of the window, and you can count the reflections of the number of panes. Keep in mind there's going to be a deflection back to the other side. It's going to be much duller when you do this. Only count the bright reflections. That'll tell you the number of panes. So typically a single pane's obvious, you don't need to do this, right? But once you get to double and triple and you get up there in age and you have to wear these glasses, it's tough to see that. It's tough to count the number of panes. That's a real quick, easy trick, and it works whether it's dark or light. Back in the day, we used to use a lighter. Not a good idea. Don't do that. You can burn that glass pretty easy. All right. Now shading on the outside. So any overhang that reduces the solar heat gain coefficient will have a ratio of 2, right? 2 units out, so say 2 feet out to every foot up. So if it's not a 2-to-1 ratio or more, then it does not provide shading on that window. So as an example, this is a picture on the left of my house. I have a nice farmer's porch. I love it. I get yelled at for not using the furniture out there enough during the summer. But you can see we don't have shading on this window internally because I have an 8-foot porch that sticks off the front. It's about a foot up, but 8 feet out, and it provides awesome shading for those windows. If I didn't include that, the gain on this window alone would drive the heat gain up drastically for that room and the total. We have to make sure we account for not just internal shading, but exterior shading when it makes sense as well. Now, counter to that is my daughter's bedroom on the second floor on the right-hand side. And you can see there's a decent sized soffit that sticks out, right? But because it doesn't have a 2-to-1 ratio or more, you can see it provides 0 shading. You can see the shade line not even hit the window, okay? Also, don't forget about the foreground. What's on the other side outside? Most of the generic values in Manual J actually have a mix between grass and crushed rock. That's kind of the generic setting. But keep in mind, if you're out looking at a concrete parking lot or water, then you're going to have a lot more deflection of the sun, let's say if it faces west in the afternoon during peak demand. And you have to make sure you account for that deflection and the additional gains on those windows, all right? That's accounted for in the foreground. Oh, don't forget about the orientation of the house. This is easy to fix in some software programs like RightSoft or things like that. I always forgot about this. One of the best things that happened to me was Google. You can actually just enter the address and Google Maps always pops up with north vertical, right? It's really easy to figure out afterwards. But typically, we just identify which direction the front door faces when we're doing a site survey so we can get the direction of all the walls right. So we understand the orientation as we're entering it, okay? All right, let's move over to internal loads. It's really important, actually, it's an older picture of my in-laws and my family here. My in-laws used to live with us. It's always surprising every time it pops up. Keep in mind, we don't size a system for the number of people that somebody might actually have in a house, or for entertaining or something like that. It's always number of bedrooms plus one. We're sizing the system for the home, okay? That's assuming there's 2 people for the master bedroom. And this is something that building inspectors do look for, right? We don't want to make, what we don't want is someone to say there's 2 people in every room, okay? It's just not the case. And when you're doing a room by room load calculation, you want to make sure you add the people to the room that they typically are during peak demand. It's usually 4 or 5 p.m., right? When it's the hottest. So that way we can account for the airflow that needs to go to that room when we actually size the distribution. Now, there is an exception to that. If you have elderly guests and you turn a room that wasn't a bedroom and they live with you full time into a bedroom, then you can account for them, which is what we did. All right. Another space when it comes to internal loads that I see a lot of people miss on is appliances. And they actually miss low because they tend to just add the scenarios that are built into the load calculation software. For instance, scenario number 1 is 1,200 BTUs per hour. And that's actually just enough for your kitchen. That's it. And if you're doing a room by room, you would add scenario number 1 to your kitchen, but then you actually have to take a look at everything else in the house, like range or washer and dryer. You know, what sometimes is an entertainment room when it comes to what you would normally call a living room, right? So all these other major appliances typically can be accounted for in scenario number 2. It's your kitchen plus those things. And it's for normal usage, right? There is a third option, scenario number 3. I apologize, it's not on your slide here. Scenario number 3 is 3,400 BTUs, and it actually accounts for multiple refrigerators. And we see this a lot because people might have a freezer or a second refrigerator that's in your conditioned space that puts off more heat, and we have to account for it. But it's not just that. There's also other additional things that you can add to the room specifically, like I have a couple of ceiling fans in my living room. Those motors that are in the ceiling fan actually puts off the same amount of sensible heat as a person. It's 250 BTUs. You have to make sure you account for that. Obviously not latent. People resting is 240 latent, but you have to make sure you account for that in your heat gain. Otherwise, you're going to be dreadfully short if you don't account for, let's say, all the can lights that's in your kitchen, or the multimedia stuff that I've added to my home office that they didn't have in 1880, right? So it's really important you account for all those things that could be running at 4 or 5 p.m. All right, so just to wrap up a little bit with Manual J, and I apologize, this says max 14 temperature difference and cooling. It's a little different out there, and that's for Massachusetts, Rhode Island. But what the key thing is here, we don't manipulate outdoor design conditions, right? So don't drastically change those numbers based on the construction, based on the city data that populates in your software, all right? And don't forget to take full credit for efficient construction features like overhangs and shading, foreground. It can drastically change your load up or down, hopefully down. That's the whole point of that efficient construction feature. And if you didn't know, at the beginning, I told you I've been teaching this for about 15 years. I was very fortunate to be taught by Hank Rakowski, who wrote the manuals at ACCA. He was the PE that's on the front of every book. He actually said, because you have to stop the rounding and the decimals at some point, that there's about 20% of oversizing built into Manual J software, even on the most aggressive load calc. So if you don't do an aggressive load calc and you add more to that, you can see how it just keeps manipulating the process further and further. And we do something we don't intend to, we oversize the unit, all right? Don't add any additional safety factor. There's so much built in between this and equipment selection I'm gonna show you, it's just not needed, okay? Now, you have to make sure you're doing this on site. This is one of those things that's hard. If you're in sales, and feel free, if you're an HVAC salesperson, throw it in the questions of the chat here about how much time you take at the home. If you're going to take additional time to do a load calc and you're using extensive software to do this, like as an example, to do a room by room load calculation on my house, I did one 2 weeks ago for Conduit. I used a different program, not theirs, and it took me almost 2 hours, all right? I cut that down to just over 15 minutes with Conduit, and Shelby will talk about that at the end. But you have to add that additional 2 hours to do a room by room load calc before you figure out what the size system needs to be in order to then sell it to me, right? It would be a drastic change to your sales process. So you have to have tools that help you do it quicker, all right? And build that value for compared to people that aren't doing load calculations, or they do what we call load calc theater, right? They take all the dimensions and they say, I have to go back to my secret layer and come up with a price for you. Just doesn't build a lot of confidence with the homeowner, okay? And then actually sell that comfort improvement, because a homeowner is going to want to know, why is the system getting so much smaller? I feel like the one that's in is not working anyway. That's why you're out here, right? And make sure you're selling the cost. It is always a tough word for me. I apologize, Shelby, because I know you put this one together. Cost efficacy, right? And right sizing, right? It's really important that you're building this value and you charge for it. Don't just do it for free and give the homeowner the size to go shop around, right? Make sure it's part of your process and doing it right, so that way you can sell the right size system to begin with. And everybody has a different way of doing it. I know a lot of the local guys I've taught will tend to do a block load first, sell the system, and then go back and do room by room with the software and spend the time after they know it's what time well invested, right? All right. So before I get into Manual S, let me just talk about what's in it for you guys when it comes to selling correctly sized systems. Typically, if you're comparing efficiency with efficiency, the correct size system is probably smaller, so it usually costs less, right? If it's a ducted system, the smaller ductwork will actually cost less and it'll be more competitive as well. Certainly, compared to an oversized system, whether it's an air conditioner or a heat pump or a furnace, it's going to be more comfortable. More comfortable 98% or 99% of the year. That 1%, we're not designing to. You have to make sure you set that expectation up front with the homeowner too in your sales process. If it's the right size system, your operating cost is going to be lower, right? Of course, if you're selling a furnace like propane or natural gas, in the Northeast we have oil, right? I don't think it's very predominant over there, but there's a reduced chance of a cracked heat exchanger. It's probably the #1 reason heat exchangers crack, is because of poor airflow, because this furnace is oversized for the duct system, or the furnace is just oversized for the house. And then, of course, it reduces the load on the grid. This is why things are eligible for rebates, and why the efficiency of the smaller systems are so much higher and they get rebates, right? So really important. So before I move into Manual S, I see there's a few questions in there and hopefully a few comments, because I asked everybody to get engaged. Shelby, is there anything you'd like me to address before I get into Manual S?
Yes, indeed. Perfect timing. So we'll actually just run through. It looks like a lot of these questions are specific to sizing, so we can cover this first chunk right now. The first question from the audience was, do inspectors evaluate sizing on new systems for new homes, or do they also evaluate sizing for retrofit projects? It's a good one.
It's a great question. So this is very dependent on the town and the building inspector, right? So I can speak from personal experience here. We have 2 towns right next to each other. We have a building inspector that you pull a building permit for any change to an existing system or a new construction, right? So it doesn't matter if it's an HVAC system that serves the home. You pull a building permit, you got to do a load calc, you got to do Manual S, and he runs through every aspect of it. And then there's another one that you go down to the town hall and they go, I don't know, I'll take your money. And they don't even look at it, right? So what we typically want in our industry is consistency. And most of our dealers, particularly in the Northeast, they just make it part of their process so it's not a surprise. They do the same thing, proper system design, every time they go out. And if an inspector wants the details, they have it ready to go. It's obvious they did it. It's not, let me send it to you. I'll email it to you tonight because I got to go do it, right? So hopefully that answered your question.
Great answer. We have 3 more questions coming in. One of them is, do you adjust your calculations for more highly insulated windows?
Yes, so when you identify the windows, the calculation will change, right? So make sure, and I believe you said insulated windows, right? Is that what you said?
Yes, indeed.
Yeah, so that would be the U value of the window. So U value is the inverse of R value, right? So when you're identifying the U value of the window, that is going to impact the load. So the better or lower the U value, because it's the inverse, then the lower the heat loss and the lower the heat gain as well. All right.
And building off that, one of the other questions was, we're installing windows down to 0.17 U value in Seattle. How can HVAC and electrical load be reduced?
Yeah, so with the U value being that high, right, it can impact, so if on a retrofit of the house, it can really change the performance of the heating system and the cooling system. So obviously we want to do that sort of thing first. That's the number one thing. We always weatherize, insulate. Insulate includes windows, right? It changes if you do it correctly, right? When you change that window out, you're also air sealing. So it changes the infiltration plus the insulation value of that wall, because that window's got a higher U value. So the better the U value, the lower heat loss and the lower heat gain you're going to need, right? So then the system should be sized based on those conditions, not what it was before. It's always a struggle when the weatherization happens. It's really hard to design a system when a homeowner says, oh yeah, I'm going to replace all the windows. Most HVAC contractors are not going to take that chance that it takes them a year to actually replace the windows.
Absolutely. Last question on system sizing for now. And of course, those of our participants, please feel free to send questions as they come to you over the rest of the webinar. But before we move on to system selection and heat pumps, do you adjust for a tighter air barrier on the home exterior? Many in Seattle are now below 0.25.
Wow, that's great. Yeah, so that would be the infiltration of the home is what you're calculating, so the air barrier, right? So yeah, absolutely. That's it. And I don't know if that question was asked prior to me covering infiltration, but the setting of the infiltration of the house, if it's measured, you literally just enter in the air changes per hour. If it's not calculated, then it's educated guess. And when it's that good, you're going to see values that are closer to semi-tight or tight. Really what's important here is new construction homes actually are outpacing updates to manual J. So if you have what the target air changes per hour is, and the builder can reach it, you should enter that in your calculation, because tight doesn't do it justice. Tight is not tight enough compared to how people are building homes today.
Awesome. Thank you, Chris. Excited for the next part.
No worries. All right, so let's move on to manual S and heat pump selection. Right before I click this page, I want you to remind you, do not kill the messenger. I did not write manual S. I know there's some things we do in our industry that actually are the exact opposite of what I'm about to tell you. But on the manufacturer side, I can tell you this is really important, because we see the problems if you don't size a heat pump correctly. We're focusing on heat pumps today. Manual S does actually talk about every single other way of heating your house for whole home applications, right? So boilers, furnaces, doesn't matter if it's radiant or baseboard, doesn't matter if it's oil or natural gas, right? Or electric. I mean, it even applies to electric resistance only homes, which we should be getting away from in code soon. All right, so heat pumps, you select heat pumps based on the heat gain. All right, this is so we don't drastically oversize for the heating side, and we have such an oversized cooling application where it short cycles and we don't remove moisture, and we cause compressor failures and all kinds of bad things. And working at a manufacturer, I can say we see this at least once a month, where people install a multi-zone ductless system and they just add up the number of rooms and put the smallest size wall mounts in every room. They get the biggest condenser because I have 8 indoor units, and it's twice the size it needs to be, and it's never comfortable. And the electric bill is through the roof. And there's noise problems because of purge cycles and defrost cycles, and all kinds of these things add up, all right? So what I want to make sure you guys know is there's 2 options. There's condition A, and you'll see condition A is, it says mild winter or has a latent cooling load. We share that in common in Massachusetts and Washington. We have a latent cooling load. Unless you're in the desert part, I don't think Washington gets too much into that dryness. And then, of course, if you have a cold winter and no cooling load, no latent cooling load, which means the sensible heat ratio of the house is 0.96 or higher. Sensible heat ratio is calculated. You take your heat gain, right? It's your sensible heat gain divided by your total heat gain, right? So not including latent, right? So sensible divided by total of the house gives you sensible heat ratio. If it's 0.96 or higher, it falls into condition B. Or you install a whole home dehumidifier to handle the latent load of the house. Then you're allowed to oversize a heat pump by 15,000 BTUs over the cooling gain. Otherwise, you're falling into condition A, and the more variable a system is, the more leeway they give you. The smallest you should put in is 90% of your total load. And that's because you can zone a system with ductwork or equipment, and the needs of the house is going to change, even on a single stage system, single speed. If you have zoned ductwork, you can undersize it and still meet the needs of the house. Not drastically, though. Maximum for a single speed piece of equipment is 115% of the cooling gain. Of course, it's 90 to 120 for multi-stage, and variable speed, which is most ductless and mini split heat pumps in the market, it'll be 90 to 130% of your total heat gain. Keep in mind, you should never install an air conditioner or heat pump that doesn't meet the latent capacity needs of the house. And you don't want to drastically oversize and have all this excess latent capacity, okay? We have to remove the moisture first in order to change the temperature of the air. It's like a cardinal rule in equipment selection. If we can't remove the moisture because the system doesn't have the full latent capacity, then we should not install that system. It'll never be comfortable, okay? Unless it's like really mild, then it could probably keep up. But at your design conditions, it'll never work, all right? All right, so I'm gonna focus on that variable speed system. In order to do this math, I'm not going to walk you through to how to interpolate this data. Every manufacturer provides it in some variation. In fact, I think Shelby sat in one of my classes where I walked through like 10 different manufacturers. It'll absolutely blow your mind if you've ever done this interpolation longhand. What I highly recommend to you is you just Google ACA Manual S speed sheet, and it's going to bring up the ACA website, and you can download this Excel document for free. It's basically any yellow cell you can fill in. One thing I want to make sure you note is if you do this and you're doing this for heat pumps, make sure on line 11 is a drop down and it asks you the type of system you're actually interpolating for. Is it a single stage heat pump? Is it a multi-stage? Is it a variable speed? Is it an air conditioner or a heat pump, right? Is it a furnace? So line 11 is a drop down, select the right system so that way all these cells work for you. If it doesn't meet the max and the minimum of manual S when you type in the performance data, the cells will go red. If it does meet it, it'll go green, and you can print this off and give it to your building inspector as manual S, right? Keep in mind, you'll still need to provide the expanded cooling data to prove that those numbers are real. And then really, you're just using this to speed up the math, but making sure it meets the code, right? It seems pretty obvious here. There are 4 different tabs at the bottom depending on the type of system, and then that line 11 drop down will narrow that system in. So like heat pump, and then what type of heat pump, all right? Remember that heat pumps are sized for cooling, and if you don't know and you have a dual source, then you have to figure out what the balance point is. And there's 2 different balance points. There's going to be one for comfort, which is displayed here out of ACA Manual H, which is heat pumps. It's a great manual for heat pumps. It's a little dated, but obviously heat pumps have only gotten better since then as far as performance go. You can see this is a more traditional heat pump, what we call our grandfather's heat pump. It's not a cold climate heat pump. We have a huge defrost knee around 40, 45 degrees. You can see the performance of this home. The heat loss is somewhere around 56,000 BTUs. But at our design temperature, which is close to 15 degrees, we only get about 20,000 BTUs. So if we were to actually draw this balance point diagram out, we could calculate how much supplemental heat we need. And that would be the difference because the heat pump doesn't shut off. We keep running it. We only need to make up the difference in supplemental, okay? Sometimes it's less expensive to run a different fuel source. At your design temperatures, though, I took a look at out in Washington, there's only one fuel source that's more efficient, natural gas, at a warmer temperature than your design condition. But it depends on the system and the COP, the break-even COP of that condenser. So what's really important here, you have to know your delivered cost per kWh for electricity, per therm for natural gas, per gallon for propane or oil if that's what you have in your home. And you can actually plug into some simple math. If you go to my website, hvacproblog.com, or you just Google how low should I operate my heat pump, I tend to show up first on Google for that. You can type in or plug in your costs into that math, and you'll find out what's called the break-even COP. Keep in mind that COP is going to go down for that system as it gets colder outside. So at some point, it's less expensive to run that other fuel source. In Massachusetts, I just did this math January 1st for my manufacturer I work for. It's 42 degrees or colder for natural gas. That's because we're paying about 35 cents per kWh and somewhere around $2 a therm for natural gas. It is a much better story when you start talking about some of our municipals that charge a little less, or versus propane and oil, which is $4 or $5 a gallon. So that temperature break even is like, as low as you run the heat pump, it's more efficient, as long as you're comfortable, right? Now, if you work for a manufacturer, you probably have access to something like this. Or if you're installing Mitsubishi, Mitsubishi offers Diamond System Builder, which is free software. If you go to mylinkdrive.com, you can download it, and it does the manual S calculation for you. You actually enter in your design conditions, you select your equipment, and this could be single zone, multi-zone, all the way across the board. And if you're in the HVAC industry, you've probably seen this in the past. It'll actually calculate any additional refrigerant charge you need to add, and it provides a great stock list when it comes to accessories and line set sizes and lengths that you need to order, right? But the key here is, on the design side, this actually will satisfy your ACA Manual S requirement, excuse me, and it'll actually tell you what your heat and cool output are at your design conditions. So you can see here, at my design conditions and cooling at 91 degrees, I'm actually getting 39,626 total BTUs out of this 3.5 ton system. But at my heating side, because it's a cold climate heat pump, at 6 degrees, which is what we designed too close to Boston, we're getting 47,881 BTUs out of a 42,000 BTU system. So most cold climate heat pumps actually get a better heating performance than what the nominal size cooling is. And we actually select heat pumps based on the cooling size and capacity. So it's not a bad process for cold climate heat pumps. It gets you pretty close. You don't need a lot of supplemental heat if you do this process correctly. And the tighter the home, the closer your heat loss and heat gain tends to be, all right? So we have plenty of time here. I'm gonna turn this over to Shelby to talk about the role of technology. I think I scared everybody enough, Shelby, on all the things you need to look at in order to do this correctly. I want you to tell them how easy it can be if you use technology.
Love it. Amazing. Well, hi, everyone. I'm Shelby. As Chris mentioned, I'm one of the co-founders of Conduit Tech, and our main objective, this is not about us, but this is about how do we help contractors and pros and energy auditors in the field simplify this workflow. That's a lot of steps that Chris went to, and it takes time to learn those, and you're never going to not need the theory. It's helpful to understand how things work to be able to use technology well. But as you saw, it's a manual process, and it's funny. I think manual is a word used to describe book, but in this case, I always think of it as by pen and paper, and they are not small. Yes, Chris has a copy. I think we may have needed to send him a second one just because it was falling apart. But we are well loved. We well love our books around here. So when you think about technology and tools, and we actually, this is just about design and sales, but on every single element of home performance, there are technology and tools that are emerging today. I'll talk a little bit about design and sales because that's what today's about, but pen and paper is sort of how things have been done for decades. Complex modeling software emerged in the 1990s, early 1990s, late 80s, and honestly hasn't evolved too much since then, but there has been this technology that's been available, and it requires a really sophisticated knowledge and quite a bit of training to be able to use it. And when we, my co-founder and I started looking at this space, we saw that as a enormous opportunity, but also a huge challenge for pros in the field to be able to do the high quality work that they want to do and deliver it to folks in a timely fashion that is not so cost ineffective. When you think about it in this industry, and any industry, time is extremely valuable from an opportunity cost perspective and from a billable hours perspective. And so that's what led us into how do we automate more of this work, never replacing the person in the home, because there's so much around observations and building data that's just frankly not available. But how can you streamline everything else that's manual? And so this is where we started using LiDAR imaging to be able to scan homes, build out 3D models, build out floor plans, and then automate the load calculation process. So it's a question of what are you observing in the home, starting with property data, but what are you observing on top of that that you might want to change, and then combining that with a user-generated floor plan and 3D model that adequately takes into account a lot of the important factors that Chris mentioned. So size of windows, the direction and orientation of that space, whether there's overhangs or not. A lot of that we can see directly just by scanning the home and building out that model. And so on the next page, what you'll see is just a quick clip of what scanning looks like. And this is where there's so many different forms of technology you can use today. But on the load calculation side, being able to model out the home is extremely powerful, because all of this is based off of what is your surface area of walls, what is your area of windows, what are your orientations of them, and then what are the materials that compose each part of that building component. And being able to overlay the two both makes it a accurate calculation, but also integrates it into an engaged customer experience. And I think something that we are all thinking about on this call is, how do we make this tangible for the homeowner? How do we help them understand what good quality work is and what they should be considering? Coming back to Chris's point about windows, if there's a window upgrade coming, you should be having a conversation with the homeowner about it, but it's so easy to skip that when you are not running a full calculation and not thinking as fully about the process. So that's what led us into this space, and that's what keeps us going. I believe this might be our last slide before we go into any additional Q&A. So thank you everyone for listening in. We have one question that, this is more of a comment coming in from Eric Miller, just that latent is not as much of an issue in the Northwest, but systems should be sized on heating load, which is super helpful to hear. Chris, any other thoughts on some of these like regional elements to consider?
Yeah, so really important. If you're sizing a system based on the heat loss, you have to make sure it doesn't drastically oversize on the cooling side, or you're going to end up with some of those problems. It's good that you don't have a latent issue like we do on the coast, on the East Coast. It's going to really reduce the likelihood of that. But it there's a point where the system doesn't ramp down to one BTU, right, or 1%. There's a ramp down there, and if it doesn't get low enough during mild conditions, it'll short cycle in mild conditions and create those problems. So some of the things we've seen to help with that, if you're sizing to the heat loss with a heat pump, some of the things I've seen in particularly Northeast is they'll actually put the core of the home on one single zone system that's variable speed, because that's where it needs the most heat in order to live in the house, right? And it has more variable capacity with a single zone system. And then let's say they'll put like all the rest of the bedrooms are all upstairs on a multi-zone or something. That tends to be the approach that people are getting the best efficiency and comfort out of without drastically oversizing for the other season.
Thank you, Chris.
No problem.
Well, any other questions coming in from the chat? We have one more from Samantha Olson. Are temperature tables being adjusted for climate change? Seattle is having some extreme heat events. Yes, indeed.
Yeah. So the tables that tend to be adjusted and using trailing data are the ASHRAE tables like that Conduit uses. Manual J does not get updated as fast as you think, and it's also rounded to the whole number. So it's not quite as accurate. It doesn't sound like a lot, but remember I talked about decimal points and where you stop, right? Because of all of that rounding, they don't go down, they round up based on temperatures, right? And it creates a bigger and bigger system. So yeah, climate change is becoming a real serious issue. From what I understand in Washington, it's not necessarily about temperature, and it's more about smoke and wildfires. And now you have a cooling need because you can't open the windows like you normally would during those seasons. You know, the drastic differences in temperature aren't as bad as you would think. But the 1% of the time it is above your design, sometimes it's a higher degree, right? Instead of it being 100 today, it might reach 105, even in Massachusetts, which can be dreadful. And I was a service manager. I've been there. I know the feeling and I know the concern. The key is you set the expectation up front, and they understand what you can and can't cool to, because you're not going to get 65 degrees even at your design condition. The system will freeze up, right? But sometimes that's what people want because they're used to a chiller or going to the movie theater or working in an office, right? We've all found out our homes aren't as comfortable as we thought they were over the last few years.
Definitely. Awesome. Well, those were all of our questions. Thank you so much, everyone in the audience, for participating. And over to Katie.
Sorry, I went short, Katie. I thought I had
Oh,
more
that's okay.
content than that.
And I actually have a question for you.
Sure.
I work for Seattle City Light. You know, I've worked in conservation, the lighting design lab. Ironically, we've got very poor lighting in this room. You know, our mission is to help, well, historically lighting contractors, but now we're expanding to whole buildings. Everything's connected now.
Yeah.
Uh, do the best work they can for customers and help the utility and the area save energy. So I have sort of a two-pronged. I had a ductless heat pump installed several years ago now, used the City Light rebate. The contractor was great. Anecdotally, for any contractors or sales staff in the audience, I did go with a contractor that was slightly more expensive because they did do a manual J calculation, took the time. But while I was listening to this presentation, I think I remember correctly, our home is a 2-story, 800 square feet, 800 square feet. It's all heated, but we were just occupying the upper and renting the lower, and we're going to use the ductless heat pump for the upper. So
Yeah.
they used only calculations on the upper, even though the whole house is connected.
Yeah.
All that said, what can we do as energy efficiency staff or advocates for residential customers to make sure these tools are being used um, the best way possible?
Yeah. So I bet the lighting team is probably not going to like me saying this, but we started with incentivizing the contractor to do load calculations, and we actually would provide an incentive if they downsized an existing system. We knew all of these systems in the Northeast were a half a ton to a ton too big. It's kind of an industry standard on all the testing that's been done out there versus an actual load calc, and sometimes more than that, right? So what they would do is they would take pictures of the existing system, provide a load calculation. Obviously, the system has to meet the rebate level, and there would be an additional incentive paid to them to install the right size, smaller system. So that way, it kind of offset the additional work they had to do to learn how to do load calculations, make it become part of their process, to feel like they're getting paid to spend the additional time out there that wasn't part of their process before. So that's probably one good approach. The other side, I hate to say it now the HVAC contractors are going to get mad at me, right? Educate the building inspectors. That's what we do decently in Massachusetts. I'm part of a nonprofit organization. I'm on the board of ACA New England, and we don't just do training for HVAC contractors. We actually do training for building inspectors, so that way they know what they're looking at and they know what to ask for, and they're not, just avoiding it, right? Because a lot of building inspectors are not mechanical inspectors. They've never been in that field. And it's like that across the country, unfortunately. Unless you're in California. California's the whole world. Shelby knows, she's worked with contractors out there. But
Yeah, I have two thoughts actually building off of that. So there are programs in California that are incentivizing people actually to do load calculations and paying contractors to start getting into that flow and compensating for this often unbillable work. And then the second thing that I was going to mention is just around training. I think that this is one of the reasons, I mean, this is one of the many reasons we love working with Chris, is that his entire belief is to put more content and training out there to make this more accessible. And I think that is offering these trainings is really, really powerful to be able to at least provide that theoretical knowledge. Why does this matter? Why is this important? Because I think a lot of folks, and we see this all the time, a lot of folks don't know what they don't know, and they know what they've been taught, not because of anything wrong or anything like that, but you learn the way the people above you teach you. And if they are doing it a certain way, you're going to learn that way first. And so making training resources more available and more accessible is definitely a mission that I know Chris has and that we share.
Yeah, speaking of that, not a slight shameless plug, Katie, if you don't mind, you can learn something for free today if you go to my YouTube channel. There's over 150 videos on there, so feel free. I'm sure Shelby can pass along the link or whatever, but no obligation. You can just search some aspect of Manual J. I'm sure I have something on it on there for free for you guys.
Yeah, and as we booked you for this, I was like, I've never heard of this. I'm not an HVAC professional, but I've never heard of this. So I looked it up and oh my gosh, it's a huge resource.
Thanks.
Yeah, and you know, I found this presentation very engaging and informative. That was really great. So thank you, Chris and Shelby, for being with us today. I put up the slide again for rebates for anybody that is interested. When you get the slide deck, all of these links are clickable. And I'm going to give a couple more minutes maybe for more questions coming in. But beyond that, thanks for being here, even though, it's a little bit later in the day for both of you. But all of this was relevant, even as a non-HVAC pro or installer or anything, and just as a homeowner. It was nice to hear these things exist and how your house is built matters.
That's for sure, Katie.
Yeah. All right. I think we will end there. Oh, Heather had a real last minute question. Which software is it?
First question is, what was that software? Well, the software that we work on is Conduit Tech. We're the ones that build. And where do you find it? You can go to our website, getconduit.com. That's at least the software we work on. And then in terms of Chris Morin's resources that he offers for free training resources, that's going to be HVAC Pro Blog. And you can find that on YouTube and on his website as well. That'll link out to all of his different social channels. And I would highly recommend, that's how we first found Chris a couple of years ago now. So we are big fans of those resources.
Thanks, Shelby.
Yeah, this was great. Thanks, Heather. Okay, let's end and let our side of the country go to lunch.
Thanks, everybody.
Thanks, everyone.
I appreciate it.
Thank you.